this perfect symposium and thank all the participants. So my study is mathematical modeling of spatial and temporal patterns of traffic accidents. So I will focus on the Istanbul case. My name is Gülsüm Çiğdem Çavdarlıoğlu, and currently I am an assistant professor at Isik University in Information Technologies department. So first of all, let me introduce my topic. So today I will talk about my study on modeling the spatial and temporal patterns of the traffic accidents which happened in Istanbul. So I have used geographical information systems and statistical tools and mathematical modeling tools to conduct this research. So as we know, why this study and why Istanbul, first of all. So all we know, Istanbul is a megacity with chaotic traffic and high accident rates. And actually, we need more than descriptive statistics. We need spatial and mathematical models to understand or to figure out the meaningful patterns and also to support risk-based planning. This is the data set I have used in this study. I requested this data set from Turkish National Police. So it's not an open data set, but academics can access this data set by a request letter. So the scope here is fatal and injury-related accidents in Istanbul. And there are spatial attributes such as coordinates and districts, and temporal attributes in this data set such as date, time, and weekday. And there are also categorical attributes, collision type, weather, lighting, status, and roadwork, and the first aid related to these accidents. As you see, the data set includes detailed accident records with these attributes. Now, this is the distribution of these traffic accidents across Istanbul and districts in Istanbul. Several statistics about the data set I have used. There are more than 100,000 data items in this data set, and this is a screenshot of this data set, so it's a very huge data set. There are also 54 attributes, and the duration is from 2013 to 2020. And yes, so these are the data set numerical attributes we have. So the most important attribute here is the coordinates, of course. Without coordinate information, we cannot implement spatial analysis techniques. This was the most important attribute because of that for my study. There are also categorical attributes. So this is the raw format of the data set. Of course, during my study, I have changed this data set and I have implemented several techniques to collect the attributes or to group the attributes. So these are my groups: accident group, daytime group, weather group, lighting group, and roadwork group, and first aid group, as you see here. And so let me introduce my methodology. In the first step, so this is the data preparation step and also the descriptive analysis step. And here in this step, I implemented GRANT4 before the modeling phase. So structural analysis techniques I have implemented, and discretization of the time and spatial dimensions here also I have implemented. And also descriptive statistics and visualization techniques I have implemented, and I have produced thematic maps to understand the distribution of these accidents and to understand the differences between districts in Istanbul. And also, of course, data cleaning phases at this step and pre-processing steps I have implemented to remove the missing data items, for example, or to remove the duplicated records and coordinate anomalies also. So here in the first step, I have used Python and Quantum GIS and several special function libraries, and also for clustering, for classification here, I have used these tools. So Quantum GIS maybe is the most important one. So it's a kind of free JS application. And in the second step, so it's the step for creating the spatial density function. Here I have implemented kernel density estimation and also Poisson density function I have tried to use. And this step includes estimating accident probabilities within the area I have selected. And then the third step, it's the temporal modeling. So here we may implement Fourier series and ARIMA techniques and also Markov chain models to understand the distribution. And then the next step is the spatiotemporal model step. So here I have implemented Poisson's spatiotemporal model. And then finally, the interpretation of the results and also to create the policy recommendation. In the fifth step, I have implemented several functions. So I tried to pick up the riskiest time and space combinations for the traffic accidents, and also several intervention recommendations at the temporal level and at the spatial level I have implemented at this step. So first of all, after the descriptive analysis, maybe we can talk about the temporal analysis results. So in this step, my aim is to understand what the data is telling us and to make the current situation in Istanbul understandable by visualizing it. Of course, visualizations are very crucial in this step. So here this graph shows the annual count of fatal and injury-related traffic accidents in Istanbul. So we observe, as you see, a rising trend until 2016, and also followed by another peak in 2019. So the number sharply declines in 2020. So this decline coincides with the global COVID-19 pandemic, probably. So it's suggesting that change in the mobility patterns may have had a significant impact on the accident frequency, as you see. So the next graph is the monthly distribution of the accidents. As you see, it reveals notable seasonal trends. The lowest number of accidents occur in February, and possibly due to shorter daylight hours and lower traffic density, probably. And the number of accidents starts increasing from March onwards, and also it's peaking in July. And this patterns aligns with the summer season during this time, when tourism, travel, and vehicle density tend to increase, of course. And after July, gradual decreases is observed toward the end of the year, as we see. So these patterns are important for seasonal traffic safety campaigns and resource allocation, of course. Yes, the next one is distribution by time zone. So here we have 4 time zones: morning, noon, evening, and night. Nighttime registers the highest number of traffic accidents, as we expect. So this is a significant peak, and it suggests the nighttime conditions such as reduced visibility or driver fatigue or increased risk-taking behavior. So they might be critical contributors to the traffic accidents. And afternoon, it's making it the second most dangerous period after the nighttime. So this could correspond to heavy traffic during post-lunch hours and beginning of evening rush. And the evening here, it shows a moderate count, and is suggesting a slightly safer window compared to the night and afternoon, possibly due to more alert drivers and reduced congestion after peak hours. And the morning, so it exhibits the lowest number of accidents. While this might seem counterintuitive considering the morning rush hour, so it may indicate higher driver alertness or stricter driving habits early in the day. So, and the next one is weekday and weekend comparison. As we show, as we see in the chart, so the traffic accidents in Istanbul are heavily concentrated during weekdays, with a sharp drop observed over the weekend. So this is likely due to intense weekday traffic. It's caused by work-related commuting probably, and also school runs and commercial activity in the city. So these findings emphasize the importance of focusing traffic safety measures, for example, enforcements or public awareness, and also smart infrastructure maybe, especially during the weekdays when the traffic volume and accident risk are at their peak. So, and this is the distribution of the traffic accidents. Here we have a legend. So to understand the distribution of these accidents within Istanbul, I transferred all my data sets to the Quantum GIS environment, and I added an attribute to each accident location. So this attribute is indicating the district in which the accident occurred. Then the attribute for the number of accidents was added to the district layer, and the number of accidents in each district I calculated using spatial analysis techniques. And then I produced this graduated thematic map using the obtained attributes. And here, this map shows the density of the accidents by district in Istanbul between 2013 and 2020. Yes, the next map, so I implemented kernel density estimation. So it's a spatial analysis technique, and it's used to generate heat maps from point data. And our data is also a point-based data. And I visualized the spatial density of traffic accidents across Istanbul, and I identified the high-risk areas, so the black areas, actually the high-risk areas. And to implement the kernel density analysis, again, I used Quantum GIS, and these are my parameters I used to create this heat map in this stage. And then the district level accident rates this time. In the previous one, I have used the number of the accidents, but this time I have used the accident rates. So I calculated the accident rates by district to create this rate map. And I used a formula, of course, for the accident rates. I calculated it by dividing the total number of accidents occurring within a specific district by the district population to create this rate map. And then this chloroplot map illustrates the rate of traffic accidents per capita across Istanbul's district. And rather than visualizing raw accident counts, it adjusts for population size to provide a more equitable comparison. And here, dark red areas, so they represent the districts with the highest accident to population ratios, so signaling a disproportionate risk level compared to their population size. And the light red, this one or this one, for example, they indicate lower per capita accident rates and suggesting either fewer incidents or higher population dilation. And central districts with dense infrastructure and intense vehicle circulation, for example, Şişli or Fatih and also Kadıköy. So they are prominent in higher ratio classes. And some peripheral districts, so although not always the most populated, also exhibit high ratios, potentially due to the limited road safety measures or high-speed roads, because the streets are empty. So this always happens in Istanbul. And this chloroplot map helps us to highlight vulnerable urban areas where targeted interventions, such as better signage or traffic calming measures or infrastructure upgrades, for example, we need to implement for these regions. And then at the third step, this is the analysis of categorical variable steps. So this step is very crucial for understanding the conditions under which accident increase. So because we have too many attributes here in this data set, but not all of these attributes are affecting the traffic case. Some of them are affecting too much, some of them are affecting not too much, for example. So here I tried to find the most important attributes in my data set to answer this question. Which type of accident occurs most frequently? And are there more nighttime or daytime accidents? And are there more accidents in areas with poor lighting? So each of these categorical variables provides unique insights into traffic risk environments. Combined, they have built a multidimensional understanding of when, where, and how traffic accidents occur in Istanbul. And these findings can guide targeted policy making and also localized interventions in areas of greatest need. Yes, the most common accident types are here. We see head-on collisions and side-on collisions and pedestrian collisions. So these are the most important types. And this may indicate accidents at intersections or on narrow roads. And accidents such as pedestrian collisions are rare, but can have a significant impact in terms of fatality or injury rates. Because of that, we can prioritize this categorical variable in a weighted model. So the day condition, next one. So here the number of accidents is high in the afternoon and morning hours, and moderate in the evening, and relatively low at night. So the accident rate increases significantly during the rush hour. And midday and morning hours may be the riskiest due to the factors such as work and school traffic, bus schedules, and fatigue. And this distribution makes the time zone an important variable in our model. So the weather next time, the cloudy weather and the fog smoke cases here, the most important cases related to the weather. Most accidents occur outdoors because clear weather is a more common condition. However, this actually doesn't necessarily mean that clear weather is dangerous. So it would be more accurate to evaluate the weather condition with a proportional analysis. For example, number of accidents per clear day, but this is out of my scope. And the next one is the lighting status. So there is a significant number of accidents occur in areas without lighting. And even impaired lighting appears to be much lower risk than no lighting. Cross-analysis nighttime accidents with lighting status actually may be very meaningful. But this variable, the lighting variable, may support the hypothesis that nighttime accidents and no lighting produce high risk. We can produce this information. And next one is the road work. So the absolute number is low in areas with road work, but this still doesn't eliminate the question of whether it creates a hazard or not. So it presented with a mapping analysis. It could be a powerful policy outcome for the planners if the roadcom affects the traffic accidents or not. And the next one is the first aid. Maybe this is related to the result of the... yes.
You have 2 minutes left, so could you please wrap up your talk?
Oh, okay.
Thank you.
So the first aid affects the result of the traffic accident, not maybe affects the traffic accident occurring. And these are the general results and valuable points for my modeling. I collected these categorical variables and I grouped them. And so this is the attribute grouping phase: time-dependent risk, road-related risk, and visibility, light effects, human factors, and severity criteria. And then I implemented a Poisson regression model. So it's especially useful when the outcome variable is a count, for example, number of fatalities in a district. So in our dataset, most crashes are non-fatal and fatal accidents are rate. So this makes the traditional linear regression unsuitable. Because of that, I implemented Poisson regression 1. And the model uses a log-link function. So it means each predictor affects the log of the expected number of events. Why Poisson regression was used? Because in our case, we are modeling whether a crash involved a fatality or not. Since the fatalities are rare, the other regression techniques are not suitable. And Poisson regression here gives us clear advantages. This is the distribution of our data set. So it means so our distribution is a Poisson distribution. So because of that, it's suitable. Poisson regression is suitable. And these are my technical results. I created 2 different models. In the first model, I focused on the traffic accidents resulting in death. And in the next one is the injury. And finally, if I continue with the K results, so for the fatal accidents, so these are the significant predictors, type of accident, day status, and roadwork. And the other predictors are not affecting this case. For the injury accidents, only one statistical significant predictor I figure out. So this was the accident type. The accident type affect the result. And these are my numerical results and their interpretations. And I indicated also these features are significant or not for the fatal accident and for the injury accident. So this is a summary table. Yes, so as I said before, the Poisson regression was a good choice for my case, and it produced not a good model, but actually I could figure out the most important factors affecting the result of the traffic accidents. And in the future research, so we can include high resolution sensor data, and we can expand temporal resolution, and also we can include driver specific behavioral factors with using smart infrastructure techniques to get better insights from this data set. So I tried to summarize for